Hey boys and girls, we're doing a little conic section review here. I'm sure you remember loving these last year in Algebra 2, but I also like to just quickly talk about why they're called conic sections, because remember, if you start with a cone and you slice it at different angles, you would get a different shape exposed on the face, or in other words, a different section. So if you were to take a cone and slice it this way at an angle, the exposed part, like if you were to put it on a deli slicer and shave it off, you would get slices that were in the shape of a parabola. Okay, so that's the most common conic section probably. You learned that in Algebra 1 even. So in this HK or vertex form, this should be pretty easy. The vertex is at -2, -5, -2, -5. Oh, excuse me. -2, +5. Whoops. And I'm not going to bother editing it out. We'll keep it real here on the math channel. And it's opening downward because of that negative coefficient. So it would be opening down. If you want to plug in points and get specifically where they are, they would be here, here, here. And that's good enough, usually 5 points. Okay, this is just a little review of some of these major qualities. I know you can plug in points if you really want. This right here, the kind when it's now y that has the quantity that is being squared and x is not being squared, that's a parabola, but it's going to be a sideways parabola. So this vertex, follows that same pattern of, hey, when it's on the inside, it's whatever makes that 0, and that would be -1, but that would be the y coordinate of the vertex, and then whatever constant you see here. It's like that. Some people also write it this way initially, if it were written like this, where that -2 were added to the other side. Some people like it that way, so you can always say, hey, it's always the opposite. Whatever makes it 0, whatever makes it 0. But either way, you're dealing with a vertex at -2, -1. And it's going to be going sideways. The lead coefficient is positive, so it's going to be going to the right. You can plug in points if you like to get exactly where these are. And we do our best parabola drawing there. Nice. Pretty good. Okay, now to the next easiest one is the circle. If you slice a cone perfectly parallel to the base, so horizontally and parallel to that circular base, at any given spot, you're just going to get a different sized circle that's exposed on the cone. Closer to the bottom, bigger circle. Close to the top, small circle. We love the circle in standard form because we can see the center right here. It's going to be at -1, +2. And remember, this constant that's isolated on the other side represents the radius squared. This shouldn't really be a big stretch, which is why I might be going through this kind of fast. But this is going to be a circle with a center at -1, 2, and then a radius of 4. So I don't feel like getting out the old compass here, so I'm just going to go 4 units in each direction from that center. 4 to the right, 4 straight up, put you at 6, which would be right about there. 4 to the left, which will put you at -5. 4 straight down, which will put you at -2, and then we just do your best. There we go. That's the perfect circle. Yep, perfect. Absolutely. And take a look at number 4 here. Not so nice because it's not in standard form for you. So we're going to have to complete the square to make it look like this with this double quantity squared, the standard form. And if these were all mixed up, by the way, you would know this was a circle and not one of the other sections because both x and y are being squared. They're being added to each other. If they were being subtracted, it would be a hyperbola. And they have the same coefficient, whether it's 1 and 1 or 2 and 2. But if they have the same coefficient, that means you're stretched the same amount in each direction horizontally and vertically, meaning you get a nice perfect circle. So that's how you would know if they were mixed up. But let's do a little completing the square review here. First, move any constants to that other side of the equation, and I'm going to group my x terms and my y terms together. So I'll have x squared minus 4x, and then I'm going to leave a little space for my completing the square. Then I've got y squared plus 6y, then I'm going to leave another little space to complete that square. And I've subtracted 4 from each side, okay, to isolate the constant on the other side. And now here's where we complete the square. Plus blank, and whatever you add here, you got to add to the other side of the equation, plus blank. And then I'm going to add something here to complete the square, and that's going to be another plus blank over here. Remember this, you're trying to make a perfect square trinomial, so that would be negative 4 divided by 2 is negative 2, and negative 2 squared is positive 4. If you add 4 here, you got to add 4 here, because now this should factor to what multiplies the positive 4 and adds up to negative 4, negative 2 and negative 2, or in other words, x minus 2 quantity squared. Plus the y quantity, 6 divided by 2 is 3, and 3 squared is 9. Add 9 to the other side to keep that balance, and now this will factor to y plus 3 quantity squared. Gather all these constants together, kind of nice, the negative 4 and 4 cancel, leaving you with 9, and now you got it in standard form. The center is going to be at positive 2, negative 3, whatever makes those inner quantities 0. And the radius, remember, is the square root of this constant. We got a nice perfect square again. How nice. We must have just got lucky. And 2, negative 3 is that center, and our radius is 3. So 3 straight up will be actually right on the x-axis, so will be tangent to that x-axis. 3 to the right, 3 to the left, 3 down, and you do your best circle. If you're really OCD, you can get out a compass or some kind of stencil, but I'm good with that. I'm accepting myself these days. So we'll move on now to ellipses. All right, here's where it got a little bit weirder in Algebra 2 last year. An ellipse was if you took a slice, but it wasn't perfectly parallel to the base. If it was at an angle, then you got kind of an oval or an ellipse shape. So this is called the standard form of the equation of an ellipse. Again, you've got x and y are both being squared, and they're being added, similar to a circle. But if you'll notice, they have different denominators or different coefficients, which means you're getting stretched more in one direction than the other, which is what results in that elliptical shape. Okay, so this is where I don't need you to remember every little bit about an ellipse, but some of the properties are going to pop up in the next chapter, which are helpful to be brushed up on. So one is when it's in this form, you can see the center the same way, and that would be 2, 0, looking at those squared x and y quantities. Now an ellipse doesn't have a single radius because it's stretched more in one direction versus the other, but it does have these, and these are related to the major and minor axes of it. So here's one thing you might recall. The bigger quantity is under y. That means we're going to be dealing with a vertically stretched ellipse. And this right here they would call a squared. I don't really care what you call it, but the a value is 6. The square root of that is kind of like the vertical radius, similar to how r squared is expressed in the circle. And this right here, the smaller quantity, is your, it's under x. That's your horizontal sort of radius. That's b squared, so b is the square root, or 3. This is about as much as I really need you to remember. The center is 2, 0, and this would be a vertical radius, if you want to call it that, of 6 units. 6 units up, 6 units down, and that's what we called the major axis, was 12 units long, kind of like the long diameter. And b equals 3, that would be 3 units to the right and 3 units to the left. The minor axis is 6 units long. You do your best to draw an ellipse that kind of goes through there. Yep, this is perfection. All right. And that's good enough. You also talked about some things last year, finding what were called the foci or foci, depending on how your teacher likes to say it. I prefer foci. Look it up. It's the primary pronunciation, but they're both acceptable. And they would be along the major axis, and they would probably be like right about here, and they had that relationship of, a squared minus b squared equals c squared, where c was the distance away. But we don't need that for what we're doing, so feel free to look it up if you want to brush up on it, but it's not going to come back to bite you this chapter. Number 6, it's not in standard form. Standard form for an ellipse is when you have 1 over here, because you don't have just a single radius like a circle, so you don't want anything over here other than 1. So if it's not 1, we're going to divide by whatever this is to make it 1. When I divide these two sides by that 100, you reduce. And of course you can have problems where you're completing the square with ellipses too. That's not going to be a big issue. Mostly just trying to brush up on a lot of little general properties here. And when we put that in the standard form, now we can see the bigger quantity is under x, which means I'm going to be dealing with a horizontal ellipse. That's the a squared now, so a is 5. This denominator is the b squared, or the minor, half of the minor axis, and that's 2. Our center is looking at these squared quantities, -3, +1. So I'll plot that -3, 1, and I will go 5 units in the x direction, 5 units horizontally, and that should give me a horizontal looking ellipse. So 5 to the right will put me at +2, 5 to the left will put me at -8, so just off the graph here. And from that same point, 2 units up and 2 units down. Okay, so now we have that. Beautiful. Horizontal ellipse, major axis of 10, minor axis of 4. And we don't actually, well, we could encounter some hyperbolas in the next section, but they're definitely not going to be as prevalent, so I didn't include any major properties or problems with them. But just in case you were kind of curious, because you had forgotten a lot of these, when you sliced a cone perfectly vertically and considered a vertical cone sitting like that, you get these 2 slices, and they are together what's known as a hyperbola. So there's that. So those are all the ways to slice a cone, and the major difference, no pun intended, is that if you have a minus between your x and y being squared. So both x and y are squared, but it's a subtraction, it's a difference instead of a plus, so it's not an ellipse or a circle. And then if it's the x squared quantity first, with the positive coefficient, you'll get a horizontal hyperbola. If it's the y squared first, or with the positive coefficient, you'll get a vertical hyperbola. And they had all these cool little properties like these asymptotes and things like that. But anyway, I digress. So hopefully you had fun getting back in touch with your old buddies, the Conic sections. And if you have any questions, as always, feel free to email me. See you later. Hope all is well.